All right, let's go ahead and get started. I got 10:10. So the last couple chapters we've worked on basically been all these different techniques on how to do integration. Starting a new chapter today, chapter 7. Chapter 7 is basically about the sorts of things you can do with integration now that you have those techniques. So we're going to go back into area. Area, I think, is something you've talked about at the tail end of Calc 1, something we've talked a lot about. But now instead of finding the area under a single curve, now we're going to talk about how to find the area between multiple curves. So let's get started. Maybe. So I want to find the area between basically the area enclosed by this red region in the y-axis. So I believe by now we're pretty comfortable with finding the area under a single curve. Now I want to find the area between that top curve, which is y equals e to the x, and the lower curve, which is y equals x. And the idea is how we can get that done. Go ahead. Okay, so we can find the area underneath the top curve. So that's this one. We can find the area under the lower one and find the difference between them. How do you feel about that? Okay. Are these integrals we can do? What's the antiderivative of e to the x? So this becomes e to the x from 0 to 1. And of x, 1/2 x squared from 0 to 1. So what do I get? I get e to the 1 minus e to the 0 minus 1/2 of 1 squared minus 1/2 of 0 squared, e minus 1 minus 1/2. So e minus 3/2. We okay with that? Any questions so far? So we did this with 2 integrals. Could we get away with doing 1 here? So one thing I want to remind us of is that these areas, integrals, these are based on Riemann sums. So if we kind of look at what we just did with Riemann sums, basically what we did is this. We took a rectangle that goes from the x-axis all the way up to this top curve. Find the area of that rectangle, right? And then we subtracted something else from that, right? We took a smaller rectangle that goes from the x-axis to that lower curve and found that, and basically found the difference between them. Do we agree with the way I'm explaining this so far? Is it possible to set this up as this rectangle here? Well, if I do another one further out, what is the height of this rectangle the way I'm drawing it? Right. So this upper y value is e to the x, and this lower y value is x, right? So remember, we're still finding the area of rectangles. And the way you find the area of a rectangle is what? What do you multiply together? So the base and the height, right? What is the base length of this rectangle? I know it depends on how long I drew that, but when we go to an integral, we call that dx, right? So the area of this rectangle is going to be dx, the base, times what's the height? It's basically, it's whatever that top level is minus whatever that lower level is. So based on that, and based on kind of what we know about Riemann sums, could I have done this with only a single integral? What would that integral look like? Integral from 0 to 1 of what? E to the x minus x dx. So that is something we can take advantage of to find these areas is, yes, two integrals will work. They're probably easier to organize if you keep them totally separate, but if you want to just do one integral, that's fine. Because really, this all goes back to what a Riemann sum is, and what a Riemann sum is the area of rectangles. Finding these areas is, I can still treat this as just one rectangle if I do that difference in their heights. Any questions so far? So this is kind of what I've generalized for you here. If I want to find the area between two curves, so between two curves over some interval, yes, two integrals will get you there, but really you can get away with one. You can get away with expressing these as one in general. Any questions on why we can do this? So if that makes sense, let's do this. Okay, now I want to find the area enclosed by these two curves. Any ideas on how to start finding that? So I'll write down the thing I just showed you. So the area integral from a to b of the difference in these two y values, these two functions. So in general, we can set these areas up this way. How can I do that specifically for this pair of functions? Do I have any of this information yet? What do I already know? So I have my two functions, f of x and g of x. So I can start setting up that way. Do you have a question? How do you know which one you set? That's a good question. Does it matter, first of all? I got some votes for no. Go ahead. Like, it doesn't matter that if it's f of x or g of x, but does it matter if one is the top function and one is the bottom function? That does matter. So I should find that out first. Because let's go back here. I showed you a picture of this one, but let's say we went the other way. What if we did the integral from 0 to 1 of x minus e to the x dx? What would that have given us? It should have given us exactly, what did I get for the first example? E minus 3 halves. So this should have been exactly 3 halves minus e. Because basically I switched the functions. I'm taking the integral of the opposite thing. Another way I can show this is this. Would we agree that this integral I already wrote is the same as this? Negative the integral from 0 to 1 of e to the x minus x dx. Basically, I factored out a -1 from inside the integral and brought it to the outside. So is 3 halves minus e positive or negative? 3 halves is 1.5, e is about 2.8, 2.7. So that'll give us a negative number. So a couple things to point out there. You will get a negative number, which doesn't make a ton of sense for area, but it will be the exact opposite of the area you want. So numerically, you'll still kind of have what you wanted, but let's try to be careful about this. It doesn't really matter which one I call f or g, but it does matter which one I'm subtracting from the other. So can I find out which one of these functions is the greater of the two? Because basically like the way Bella put it, which one's the upper curve, which one's on top. That's the one I want to put first. How do I find out which one that is? I could graph it. I could plug in some values. Does it matter which values I plug in? Yes. Why? Right. So I will tell you right now, without giving you any more details, this graph sort of looks like this. Something like that, right? So it definitely depends on what x values I choose, because that'll tell you the curve is a different curve is above the other. But I don't care about this thing for all values of x. I care about a certain interval. So one word I want to impress upon you all here is this: the region enclosed by these two curves. So basically there's some like closed bounded region that is kind of surrounded by these two curves. So how can I find where that is? I can set them equal to each other, because what's going on the left here, basically I'll have this. I'll have some left boundary and some right boundary. And the way I can find that is by setting these equal to each other. So x squared equals 2x minus x squared. Where should I go from here? What's that? Sorry, you want to go from left to right or right to left? Okay, so if I do that, I get 2x squared equals 2x. What does that tell me? Or where do I go from there? So 2x squared minus 2x equals 0. And then you wanted to pull out an x. So equals x times 2x minus 2. So that gives us x equals 0, x equals 1. So I did a lot of algebra pretty quickly, so let me stop for a second. Are we okay with how we got those two x values? Go ahead, Phil. It's a good question. Let's talk about that again. Why did we have to set those equal to each other? What information came out of that? Clement?
It says to find the area of the region the two functions. So where it's enclosed, the functions kind of overlap, and at that overlap.
Right. So let me start this graph over, because the way I drew it was more inaccurate than I wanted. So I have a good idea what y equals x squared looks like. That is this parabola that opens up and goes to the origin. What the other one looks like is basically it also goes to the origin, right? In fact, we just learned that. We learned that these things cross at x equals 0 and x equals 1. So basically what's going on here is something like this. Maybe we can make this a little more accurate by, so we got the x values, right? X equals 0, x equals 1. What are the y values that go with it? I think when x equals 0, y equals 0, right? For either one of these curves. So we know these two things cross at the origin. What about when x equals 1? Is that the point 1, 1? So here's what I know. I know that these two curves cross at these two places, the point 0, 0 and the point 1, 1. Let me ask this. I don't have these two things ever crossing again here. But is it possible for them to be crossing somewhere in between 0 and 1? Is that possible? I say no. Because if there were other places, then I think this right here would have found them. So we solved a quadratic. We know that quadratics have two solutions, which means we found the only two places where these things could have met. So we found those two places where they met. We know they never have, they go to the same point anywhere else, which means there has to be some kind of like closed area in between them. Are we okay with that? Did I answer your question, Bella?
Yeah.
Okay. Good. So now that we have that region, have we learned anything else about how to set this integral up? Are we sure about 2x minus x squared being the upper one? If you agree with the way I drew this graph, then yeah, we can say that. So 2x minus x squared minus x squared, that's the integrand. That's the thing, that's the function we're going to integrate. We still need the bounds. Do we have those? That should be 0 and 1. So from the algebra we did to figure out where they meet, I think that gave us the boundary. What if I didn't draw you a graph? Is there any other way to figure out which curve goes on top or which function goes on top? Now that we have the bounds, so yeah, we could try a bunch of x values, but without knowing which ones we really care about, that wouldn't tell us a lot. But now we do know. So what's a good value to choose? So let's do that just to confirm. When x equals 0.5, then what is x squared? 0.25. And what is 2x minus x squared? 1 minus a quarter, so 0.75. So I think that confirms that the way we set this integral up is correct. So the graph and the one little test point we took, those agree with each other. So basically, and this is kind of going to be common for a lot of the things we do in this chapter, is this integral right here going to be very hard to do compared with some of the things I asked you to do a week or two ago. These integrals aren't hard, but now we have to set them up. So that's where the kind of intellectual work comes from, is not in doing the integrals as much as getting them. So I want to talk about how we got this integral as much as we need to. Any questions about how we set this up before we compute it? Okay. So what should we do to go forward? Integrate now? All right, so if we integrate, we get what? X squared minus 1/3 x cubed minus 1/3 x cubed. And I want to evaluate that from 0 to 1. So very convenient numbers, 0 and 1. So that should be 1 minus 1/3 minus 1/3 minus, I think when you plug in 0 to all those, they all get 0. So final result is what? 1/3. Are we okay with that number, 1/3? Is there anything else we could have done to integrate that? So if like terms combine inside the integral, you are absolutely welcome to combine them. So this would be 2x minus 2x squared. Are we convinced that would have given us the same result? It better have. And it would have. So another thing to look out for, by no means mandatory, but it might save you a few seconds. It might save you a little bit. Any questions here? Okay. go again. How about this? Any thoughts on how to get started? Want to convert the y squared? So y squared equals 3 minus x. How does that convert? Close. It's one thing we got to, yeah, it could be positive or negative, right? But yeah, we can do that. So now we got y equals basically these two things that I'm kind of compacting together. Good. What else? Yeah, I think we're going to have to do it in pairs, though. So let's do this. The square root of 3 minus x equals x minus 1. And also negative the square root of 3 minus x equals x minus 1. Can we solve both of those? Where do we go from here? If we square both sides, what do we get? 3 minus x equals, so this was going to be 3 minus x as well. What's the right-hand side look like? X squared minus 2x plus 1. I think from here, these are going to end up giving me the same solutions. So I'll drop one. All right, how do I solve these equations, or this equation? What kind of equation is it? Quadratic. So in order to solve a quadratic, what should I try to do? Right, so I want to set this thing equal to 0. So let's move everything over. X squared minus x minus 2 equals 0. Does that factor? X minus 2, x plus 1 equals 0. So x equals negative 1, positive 2. So what have we learned? I think we got the bounds of our integral, right? What else do we need to do? Try a value between them. So what will a value between those tell us? Which one's the greater function? So when x equals 0, I get x minus 1 equals negative 1. And what do I give the other one? Y equals plus or minus square root of 3 minus 0. So I get two y values there. So I think this is something we have to be careful about. So how many points of intersection might I have gotten here? It seems like, or wait, no, this is not a point of intersection, but
the negative square root of 3 out of our bounds.
Is the negative square root of, well, what is this negative square root of 3? That's a y value, right? So those y values are, okay. Yeah, those can be as large or small as they are. But did this tell us what we want to know about which curve is on top? Radical 3 is bigger than negative 1, but radical 3 is less than negative 1. So maybe we should draw a graph. Do I know what these things look like? I think I know what x minus 1 looks like. I feel a lot more confident in that than I do about the y squared one. But we'll break that one down. I think it's going to help that Clement had us basically break it into two different pieces. So y equals x minus 1 is going to be a straight line that goes like this. So let's talk about the square root function. What does this look like? Y equals radical 3 minus x. Because if I can figure out what that, or if I can piece together what that looks like, I can kind of reflect it over the x-axis to get the other side of it. It's exactly a horizontal parabola. Where does it touch the x-axis? Should be at 3. When we think about parabolas, usually we think about them opening up or down, right? This is horizontal, so it's either to the left or right. Which way should it be? Does it make sense for x to be bigger than 3 in this equation? No. So I think it has to open left. I don't think there's anything going on to the right of it. So it's going to look like this. And the negative side is going to be mirrored. So it's going to look like that. So I have intersection points here and here. So any questions about the graph we've built so far, where those intersection points are? Can we start setting up the integral? One thing I want to point out, though, is this. Let me draw you two rectangles here. I'll draw one here and one here. The rectangle I drew on the left, how do I find the height of that rectangle? Like, what's telling us what the top of this rectangle is? So I drew it up to the x-axis here. Why did I draw it with the top of it here? I draw it off the x-axis to show that doesn't really have anything to do with it. I'll draw it further left. So back to my previous question. Why does this rectangle stop? Like, why does the top of this rectangle stop here? No higher, no lower. So the top of that rectangle, like no matter where I draw it over here, the top of that rectangle is going to be, like the top border of that rectangle is going to be y equals x minus 1. What's the bottom border going to come from? Negative square root of 3 minus x, right? So there are lots of rectangles I can draw over here. They're going to have the same top border and bottom border. What about over here? Right. So there, the bottom border is going to be negative radical 3 minus x no matter where I am. But after this point here, I'm going to have a different like top border there. So because of that, I'll have to set up two integrals, which you could do, but you can also avoid. So let's talk about how we might avoid that. I mean, almost all the integrals we've done, maybe all the integrals we've done have dealt with these vertical rectangles. What if I set it up like this, where I have these long rectangles that have very, very narrow heights, but very long lengths? Now, instead of me talking about the upper and lower borders, let's talk about the left and right borders. No matter how high or low I draw this rectangle, is it going to have the same left boundary? What's that left boundary going to be? X minus this, the straight line, right? What's the right boundary going to be? It's going to be that parabola, right? So because that is going to be consistent no matter how high or low I am, I can get away with using only one integral. So now let's, instead of setting up an integral exactly like we're used to, let's do it this way. From y equals a to y equals b of f of y minus g of y dy. Basically, we're still setting up a Riemann sum. We're still going to find the area of a bunch of rectangles. It's just now those rectangles are not going to be vertical and have a very narrow x length. They're going to be very narrow and have these long horizontal lengths. But we can still set up a Riemann sum that way. But we got to be a little more careful about how we do it. So the question we asked for the last couple examples is, which curve is what curve's on top, or what's the upper curve? Let's generalize that a little bit. Let's get away from saying which one is the upper curve and which one's the greater curve. So when you're looking at y values, greater values are above lesser values, right? If you're looking horizontal, where are the greater values going to be? To the right. So in this situation, I want to know what the greater curve is, because that's going to be the one where? What's the greater curve going to be here? It's going to be that y squared, right? So the greater curve is going to be the parabola, and the lesser curve is going to be the straight line. Are we okay with that, first of all? Now let's talk about the bounds. The bounds are y values, right? So can I figure out what my bounds are going to be? Or have I already maybe done it? So we found intersection points, but I found x values. All right, I can plug those into the function and see what the y values are. And I think we already did that for, oh, maybe we didn't do it. Oh, no, we tested a point. When x equals -1, what does y equal to? Y equals -2. Does that agree with both of them? It should. Because you get plus or minus 2 out of the y squared one. When x equals 2, what do I get? 1. So now our integral can be set up like this. The integral from -2 to 1 of what's the greater function. So here's the thing, the greater function is the parabola, right? But now we want to write these functions not as like expressed in y. We want to write them, sorry, not expressed in x, we want to write them expressed in y. So what do I need to do with this y squared equals 3 minus x? I need to solve that for x. So try to carve out a little corner here. Y squared equals 3 minus x, or y squared minus 3 equals x. Oh, equals -x. And then x equals 3 minus y squared. So that's my upper or my greater function, 3 minus y squared. What's the lesser function? That should be y plus 1. So I want to stop there. We did a lot of manipulation and a lot of probably strange things to get there. So let's recap. How did we start this? I think the very first thing we'll suggest is that we take the y squared equals 2 minus x and think about that in terms of y equals, this plus or minus square root function. Did we actually end up using that? I think the biggest thing this helped with was making this graph down here. But one thing I want to suggest is if you have any doubt, or maybe just in any case, while we're getting used to this, draw a graph or go to Desmos and make a graph and see what these things look like. Try to get your bearings, try to see how to organize these things. What do we do after that? So what's this calculation here that we did? Basically, that was to find the bounds. And we originally, because we're used to doing it like this, we found bounds, or we found the intersection points in X, and we ended up trading those in for Y values to write the bounds on. So we had the bounds. We've got the bounds of -2 and 1 from there. Y values. Any questions on how we found out that 3 minus y squared should be our f and y plus 1 should be our g? Okay, the biggest thing I want to focus, go ahead.
Without actually having access to the graph, is there a mathematical way to determine that?
Determine what?
Determine which one is the upper.
Yeah, so, and I'm gonna, it's not so much upper in this case, because we're setting up functions as, one thing that's kind of hidden here is this right here is, this is an x value. This right here is an x value. I think we're very used to, when we look at f of x, we know that that's another way to say y, right? But maybe it's not clear that looking at f of y is another way to express x, because we don't usually look at functions that way. So the question was, is there mathematically a way to know which one is the greater if you don't have access to a graph? So I guess let me ask a question in response to that. Are you okay with how we found these bounds of -2 and 1? If you're okay with that, let's pretend we didn't have the graph here. We have the bounds of -2 and 1. How would we find, in a non-graphical way, which one of those curves is greater? What's a y value that I would care about? I don't think y equals 3 is one that I would go with. 0 is a good one. Why?
Pretty easy to plug in for y.
But more importantly, what else about 0 is it's between -2 and 1. So now that I know that at the bounds, those curves are going to be equal. That's how I found those points. So the way I can find which one's greater is by just choosing any points I want, any y value I want between -2 and 1. So 0, like you said, is a very convenient one to try. Let's try it. If I plug in 0 for this y and the y squared here, I get 3. If I plug in 0 in for y plus 1, I get 1. So that tells me that this thing on the left is going to be greater than this thing on the right, everywhere inside that interval. So yeah, if you didn't have access to a graph, so we didn't use the graph to find the intersection points. So you can find the intersection points algebraically by setting the equations equal to each other. And then once you have them, just try something in between your bounds. And that'll basically, whatever your test point says, that'll speak for everything on the inside of that interval. Good question. What else? So we're not used to setting up integrals in terms of y like this. Why did we decide to do it? Why did I push us in that direction? Right. So that was the most efficient way to deal with that. This square root. Basically, this square root right here is not a function of x. So after I cross like this vertical boundary line, I would have to set up a second integral, which you can do. It just takes a little more time. But that's exactly why that's exactly why I pushed us towards doing this integral in terms of y, so we could only do one integral. Anything else? Go ahead.
Is it a good rule of thumb that it's because it crosses the
because what crosses the x-axis?
Because the function isn't it both like above and below quadrants, it needs to be done with dy.
I don't think that alone is not, I don't think is going to push us, because I think if I would have kept graphing this, you know, I graphed like a square root, but it should not be. This really does behave like this. But I don't think it's so much that that the curve lives on both sides of the x-axis. Here's the thing that I might encourage you to focus on instead. Y equals x minus 1. Is that a function of x? Is y a function of x there? And let's unpack what I mean by that. What makes a function a function? By definition. It's for every one input, I get exactly one output, right? So in y equals x minus 1, no matter what value of x I give you, I will get one y value, right? Is that true for this thing? That is not true for y squared equals 3 minus x. If I give you a single x value, I might get two y values. So this thing is not a function of x. But is x a function of y? If I plug in a certain y value to this, how many x values will I get? Exactly one. So it's the fact that this thing right here is a function of x and y. Like y is a function of x and x is a function of y. No matter how you graph it, or no matter how you look at that, one input will lead you to one output. I can only say that in one direction for this guy. So I think that would be the thing that leads me to, all right, since both of these are a function of y, I would want to set up my integral in terms of y. Because that ambiguity forces us to do two integrals if we treat this in terms of x. But yeah, I would trust that. I would trust that as a rule of thumb, for sure. Anything else? Go ahead. Well, the bounds, I think we've already dealt with the fact that the bounds are going to be different, because so the x values we found were -1 and 2, right? I think we used those to get to the y bounds. The easier function to deal with here is y equals x minus 1. If you subtract 1 from both of those, you'll get -2 and +1. So I think, yeah, you do need to make sure the bounds are y values. I think we've already taken care of that. Good questions. What else? Go ahead.
Would it be wise to just kind of wrap them before?
I think so. So yeah, graphing is, I mean, especially when we're just getting started, like doing things like this, graphs are a good thing to look at to get you organized. Another thing you could look at here is, yeah, see what kinds of curves these are going to make. Straight lines are pretty easy to think about, especially in relation to parabolas, especially parabolas that don't behave the way we're used to them behaving. Think about what's a function of what. For example, we didn't even consider this, but let's go back to this here. Is this thing right here, y equals x squared, is x a function of y? No. I mean, we didn't even consider this because we're so used to parabolas opening up and down. But to set up this integral in terms of y would be very tricky. The kind of the blessing in disguise here is that we don't really even think about doing that. We're much more naturally oriented to try to set things up in x first, but sometimes it's better off to do things in y. I think this is one of those times. What else? So again, we've talked like for 15, 20 minutes about how to set up this integral and why it was perhaps better to do it this way than using x. I don't want to stop there in case people have more questions. Is there anything else you'd like to talk about with basically anything we've done to get to this point? All right, if we're not okay, but relatively okay with where this integral came from, can we compute it? How do we do that? Yeah, so what are the like terms? Is it just the constants? 2 minus y squared minus y. So I get 2y minus 1/3 y cubed minus 1/2 y squared from 1 to -2. Really running short on space now. So 2 minus 1/3 minus 1/2 minus what happens when I put in -2. I get minus 4 minus 8/3. Yeah, you're right. And minus 2. Yeah, I'm out of room. So if anybody has a final number, we can throw it out. Otherwise, I'm happy with that. That totally unsimplified string of arithmetic. Any questions there? Again. So yeah, lots of stuff that went on with that. And I think a lot of it's very tricky and a lot of it probably won't sink in until one, we've looked at more examples, two, you kind of fight with it on your own at some point. But if you have questions now that come to mind, let's hear them. Go ahead. Mm-hmm.
Does it matter which one you plug it into? Because I know you said you got the same thing.
Yeah, so that's a good question. Should you always get the same thing from both of these? You bet. Otherwise, so let's recap this. Where did these numbers come from? How did I find them? Right. So, but right, you set them equal to each other. So if you did that correctly, then it should not matter which one you go back to. Okay. So this one's way more digestible. That's why I think why that one was chosen. But yeah, it's a good question. After you find your intersection points, it should not matter what you do with them, assuming that your algebra went correct to get them. What else? All right. Back up on Wednesday. We'll see you then.